Welcome back. After a very long hiatus, I had a long, busy semester, wasn't making some videos. So we're getting back into the sheaf stuff. But before we dive in, I just want to say I'm doing things a little bit differently. I am not editing my videos. So normally, even though they might not look super polished, I edit my videos, I edit out awkward pauses and ums and ahs, and that takes a lot of time and maybe you don't care all that much. So let me know if this new style is that much worse or if it's better. And I might just stick with not editing the videos, and that might actually translate into me doing more videos more frequently. We'll see. So I just wanted to let you know about that. Let's start talking about sheaves. So let's talk about stocks. That's the plan for today. So let's recall that we had our favorite example of the real numbers and the sheaf of continuous functions, which for every open set of the real numbers, it assigned to us the not just set, but we discovered, in fact, we have a ring of functions going from u into the real numbers, right? Because you can multiply and add continuous functions, and you still get continuous functions back. Awesome. And we also came to this idea of how when we make the open set smaller, the ring gets larger, right? So, for example, we had, 1 over x. This is not a function, is not even a function on the real numbers, let alone continuous one. But on the open set, where you just remove the single point, 0, now this is a continuous function, right? So we had all the continuous functions we had before, but now we gain some new ones. And, if we shrink down, say, to the interval 0, 1, now we can have all sorts of stuff, right? Like I could have the function x squared divided by sine x. This is continuous in this interval, even though sine x has infinitely many zeros across the real numbers. I've taken an open set small enough that I've avoided all of them, right? So as my open set shrink, my functions on those open sets grow. And so keeping this theme, we might sort of wonder, well, what happens when we zoom all the way in, right? So again, this is why I'm bringing up this idea of the derivative, right? We're essentially recovering the sort of idea of the derivative, although we're going to see it's a little fancier than we might have bargained for. So here I have this point, right? And I want to know, like, what's the how's the function behaving near that point, right? When we zoom in, we see that calculus allows us to approximate functions by linear functions, right? So when I zoom in far enough, it should sort of look linear, right? So I want to see, well, what's happening to all my functions as I zoom in with smaller and smaller open sets. In the next video, we'll probably start getting to the more abstract categorical definitions of all these things, and armed with some examples and intuition, we'll be better equipped to see why that's even a worthwhile pursuit. And here, let me just as a preview, let me mention that the concept of a categorical limit, not to be confused with a limit in calculus, although you can see here's a point where they have similarities between them, is actually going to be really helpful for capturing this notion. But let's look at something perhaps a little bit more classical in describing the sheaf of our function, right? So again, I'm going to start with some point, and I'm going to consider an open set containing that point. So call this open set U, and I'll draw some lines here. And I'll consider another open set containing that point. We'll call it V. So that will go here. And suppose even further, I have an open set really inside their intersection W. And here's what's going on. So I'm gonna have a function f. F is, it's, let's say it's going to be a section of my sheaf over the open set U. And my other function G, this is going to be a section of V, right? And what's going to happen is that they're going to agree on W, and then they could maybe do other things elsewhere, right? But they're going to agree on W. So what's the point of this? Why am I even bringing this up? Well, we want to think about what's happening closer and closer to some point, right? In fact, let me mention as a side note, you might wonder, well, okay, I have my sheaf. It assigns values to things. Well, what if I just took my sheaf of continuous functions and I looked at the continuous functions at a point? Right? That seems like a reasonable thing to do. If I want to really zoom in and look at all the functions at that point, that should sort of be like the maximal growth, right? All I need to avoid are things that have a 0 at this point X in the denominator. But remember, in our definition of a sheaf, it's only assigning rings or sets to open sets, right? So I can only ever plug some open set U into C. And in the real numbers, a singleton point is not an open set, right? You can have weird topological spaces where that happens, but we want something that's going to work in the most generality, right? So that's part of why we're taking this approach, is that, well, let's sort of slowly zoom in then. I can't plug this into here, but what I can do is investigate the open sets containing this point and then shrink those open sets and see what happens. So coming back to this picture, right? I have F and G, and at first I can't even really compare F and G, right? Because they belong to different rings, right? Even though there's overlap of the open sets, F belongs to this very specific assignment over U, and G belongs to this very specific assignment over V. So, but there's something in common, right? We know, I've told you already, that they agree on this smaller open set W in the intersection. Well, since W is in the intersection of U and V, remember that our sheaf axioms come with restriction maps. So what I can do is I can actually take the restriction of F. So how might I write this? So I can restrict F down to W, and I can take G and I can restrict G down to W, right? Now, both of these live in the sheaf, the sections over W, right? These are both continuous functions off of W. And my claim is, I'm asking you to consider an example where these are equal, right? Over W. So suppose I have F and G and they're equal over here. Now remember, I'm thinking about zooming into this function. I'm going to keep shrinking the open sets, right? So F and G, I'm at W, I'm at this open set W. I can't tell the difference between F and G anymore, right? So I'm just going to keep shrinking further and further, and F and G are going to represent the same thing for me, right? As I zoom in closer and closer to X, because as I get smaller and smaller, I can't tell the difference between them anymore. So what I'm going to do then to investigate functions that are defined around this point, what I'm going to do is consider, any function F and any U. So I'll write this as a pair. Sometimes it's written in the other direction. Maybe the open set comes first. So I'm going to consider the collection of all pairs where U is an open set containing my point of interest, X, and F, of course, is a continuous function on the open set U. And I'm going to define an equivalence relation. So I'm going to say that, FU and GV are equivalent if and only if there exists some open set in the intersection of U and V such that F, when restricted to W, is the same as G when restricted to W, right? So that's just capturing this above idea that if two functions eventually look the same on some open set, well, as far as this single point X is concerned, they're going to take the same value at X in particular, right? So I'm going to treat them as the same function. And this is exactly so. First, let me lay out some terminology. So these equivalence classes are called germs, right? This is called the germ of a function. So going back to this sort of agricultural terminology, right? We're thinking about our space X. And a sheaf, it's like, we have a bunch of functions, right? We've got the sheaf has these sections of it, right? We have these continuous functions and these sort of, or rather there's like a collection, a ring of functions, right? So the ring of functions over some open set, right? It's like a sheaf of wheat. It's like this bundle of wheat, right? And the stalk, just like in a plant of wheat, that's really like the base, right? And the germs are like the little germs of the stalk. I'm not super familiar with the agricultural aspects of it, but they're these little sort of at the base of these little spindles here. So the stalk then, so the germs are the equivalence classes, and the stalk of the sheaf, which, so let me go slightly more general here now. So if I have some sheaf F on some topological space X, the stalk of that sheaf is just all the equivalence classes of germs where we run over exactly all of these open sets containing X and those sections of our sheaf over that open set. Okay, so that was a bunch of information. That's the basic of what a stalk is. And now this is our sort of stand-in, right? We weren't able to make sense of this thing in general because in general, we can't expect our singleton sets to be open. But this is the next best thing. This is the next best approximation. So I can't just have continuous functions off of this point, but what I can have is continuous functions on open sets containing that point, and I can define an equivalence relation that says that they're basically going to be the same once I make my open set small enough. Great. Okay. So that gives us our stalk, and you can sort of see, based on the way that we built this up, why this should recover some sort of notion of infinitesimal, right? I'm not going to say too much about this now. Maybe I'll go into a formal proof eventually later in the series. But one thing I want to mention is this does get related to the tangent space at a point. If, say, we're dealing with a manifold and we're looking at the sheaf of smooth functions on that manifold. So if I have some, if I have some manifold M, and I consider the tangent space 2M, and I look at my sheaf is now the smooth function, so it assigns to each open set functions from that open set in my manifold into say the real numbers, if I'm working on a real manifold, that are infinitely differentiable. And it turns out that if you take, so this is a ring, much like in our example of continuous functions. And if you take the stalk of the sheaf at any point, this ring actually has a maximal ideal, a unique maximal ideal, which is called a local ring. And actually where that terminology comes from is this, because we're localizing our functions. But okay, don't worry about that. We're going to get into that later. And it turns out, this is a little weird. I know this is probably not why is this true? And why is it not just like the Stalk or something? But it turns out if you take the maximal ideal, you mod it out by the square of that maximal ideal. This is a vector space. Namely, it's a vector space since this is a ring and this is a maximal ideal. You can take the quotient of these. And well, in this case, it's going to be a real vector space. And now you take the dual vector space. And that turns out to be isomorphic to your tangent space. Okay, if that was a lot for you, don't worry about it. We will get there. That this was not an essential thing to grasp, but just a small little tidbit of information that here's a really precise way, right? So part of our idea with this, we're trying to recapture the notion of infinitesimals and maybe the derivative. And if you know some manifold theory, you know that tangent spaces do recapture that notion. And so the theorem of this result makes that really concrete. By the way, if you're watching the series to accompany your learning in an algebraic geometry textbook, they might just hit you with this definition of tangent space, and you might be like, why? Well, this is one possible way that you could see why this is a sensible definition, because, for example, in manifolds, this is isomorphic in a very natural way to the tangent space. One last thing I want to mention before we go for today is that we talked before about morphisms of sheaves, right? So if I had two sheaves on a space, we define this morphism so that it respected, it was really an assignment of each open set, a sequence of maps, or a map for each open set, in a way that was compatible with the restriction property, right? So one of the nice things about Stalks is that it makes the analysis of morphisms nicer sometimes. So sometimes it's easier to do stuff on the level of Stalks, right? What do I mean by that? Well, if I have some morphism, right, let's call this phi. So what that says, right, is that actually, sometimes we write phi sub u. I really have this morphism between these two different sheaves on every open set. It's compatible with restrictions. And that means then that I should get a morphism of Stalks, right? This should induce a morphism of Stalks. Because here, I mean, what's an element of my Stalk? It's going to be some equivalence class where I have F and U, and F is a section, right? F is a section of U. So then what I can do is I'm going to define a map phi sub X, and that is going to, what am I going to do? I'm going to have phi sub X, and what am I going to define it to do to F and U? Well, that's pretty simple, right? I can just simply take it to the equivalence class determined by phi at U, right? Because so if little f belongs to here, that means I can apply my phi U, and that lands me in G at U, right? So, oh, forgot to write my F here. And now the thing you need to check, so maybe here's good homework, check that this is well defined, right? Because this, remember, this is not just a pair. I'm really thinking of this as an equivalence class, right? So you need to convince yourself that if you had some pair H and V such that there existed some W, which was in the intersection of U and V, for which F restricted to W was equal to H restricted to W, then that should be respected on the other side, right? So well, let me be more precise. That was a little confusing way of wording it. So if this is the case, right? So that says that F of U and H of V represent the same equivalence class. Then in order for this to be a well-defined map, it needs to be the case that applying this map to either of these pairs gives me the same equivalence class for Stalks at G, right? So in other words, I want to be sure, maybe I'll just finish the proof for you. I want to be sure, if you want, pause the video and check it out. So I want to be sure that phi of U F U is equivalent to phi of U, phi of U, or rather, sorry, phi of V at H of V, right? I want to make sure that these two things are equivalent. Well, what does that mean for these two germs, for this to be the same germ, so I get my well-defined map on Stalks? Well, I need to have some sort of set that's in the intersection of U and V, such that some things happen. Well, let's look at what we have on the screen. Maybe I should scroll up in case my video's cutting it out. Look what we have on the screen, right? What have I supposed? I have a pair F and U, well, really an equivalence class determined by a pair, an equivalence class determined by some other pair, and I've supposed that I have a W in the intersection of U and V. Well, I've already supposed that I have that W. Maybe it's going to be that W, right? So what needs to be true? It needs to be true that phi U of F restricted to W is equal to phi V at H restricted to W, right? Great. Awkward pauses. So the way to see that this is indeed the case is to consider our diagram of morphisms, right? So I have F at U, and this is where my F lives. I map it into G of U, and here I want to restrict down to F of W, and here I'm going to restrict down to G of W. Right, so I consider my diagram. Maybe I'll move this over to make life easy. So I consider this diagram, and so over here I've started with F, right? I've started with F here, and so I can either so what's happened here is I've first applied phi at U to F and then restricted. So that's going along this way. But because I've assumed that phi of U is a sheaf morphism, that's the same as if I had first restricted, right? So I have phi at U of F restricted to W, this is the same as first restricting F down to W and then applying phi at W, right? But F at W, remember, I'm assuming that F and H represent the same equivalence class, right? So I'm assuming that F restricted to W is the same as H restricted to W. So this becomes phi W. Well, this is the same thing as H restricted to W, right? I can just replace F restricted to W with H restricted to W. And then one more time, I can go through this level of sheaf morphisms, right? So now what I've done is I'm imagining I'm starting with H, and I've first restricted, and then I applied phi W. So maybe I should write that in here. But now the fact that I have a sheaf morphism, if you remember from the previous video, says I can go the opposite way or the other way around, and I get the exact same thing. So I can swap these back, and I know that this is the same as phi WH restricted to W. But that's exactly what I wanted to show, right? So we've concluded that this is a well-defined map on Stalks. In fact, you can check that this respects, your Stalks still are rings. You can show that the ring morphisms respect this equivalence relation. And in fact, you get a ring homomorphism. And so this video is getting pretty long. Maybe your patience is wearing thin. So let me just say one final big thing about Stalks that it can make our life easier, and we'll probably make use of this in future videos, is suppose you have a morphism of Stalks, phi from F to G, then this is an isomorphism. So if you have a morphism of sheaves, it's an isomorphism if and only if the induced map on the Stalks is an isomorphism for all points in your topological space X. So, for example, well, this is just another instance of the local to global principle that I've talked about before, right? So a morphism of sheaves, an isomorphism of sheaves, is this very global thing, right? It's something that has to be true on all the open sets, including, right? You need to have a map for the if you can plug your entire topological space as an open set, right? So you can plug the whole thing into your sheaf. We sometimes call these the global sections. And it needs to be an isomorphism on that level, as well as all the open sets. And we're going to say that that's actually captured entirely what's happening point-wise on all of the Stalks. Okay, so I think that's it for today. I think the flow was all right with the lack of editing that I'm going to do. Let me know. If you have any questions, also let me know. And next time, we're going to start getting into the abstract definitions. It's going to be a lot of repetition. You'll see. So maybe the next couple videos you might find a little bit boring in some sense, but the idea is to inspire why we might care about these categorical definitions. So yeah, thanks for watching.